Welcome to the 2016 Alaska Fire Presentation Series. It is being brought to you by the Alaska Natural Resource and Outdoor Education Association, or ANRO. ANRO is dedicated to promoting and implementing excellence in natural resource, outdoor, and environmental education for all Alaskans. My name is Kathy Rezabek, and I would like to introduce our speaker today, Ed Berg. Ed held the ecologist position at the Kenai National Wildlife Refuge for 17 years, prior to his retirement in 2010. He has been an adjunct instructor in geology at the Kenai Peninsula College since 1983. He has a PhD in botany from the University of Georgia. Today, he will be talking about fire and vegetation in a changing climate on the Kenai Peninsula, a 14,000-year record. Welcome, Ed.
Thank you, Kathy. This is Ed Berg speaking. So today we've got kind of the grand overview there of how the forests and fire regimes have changed since the end of the last glacial period. And then we've got some more detailed look at two fires specifically. So here is a quick overview of the subjects for the day. We'll start with looking at the last couple hundred years of fire activity on the Kenai, and then we'll bounce back and ask how does that fit in with the evolution of vegetation since the end of the glacial period. We'll look in detail at two of the big historic fires here, 1947 and 69. And we're very privileged to have permanent plot data covering the forest regrowth in the 1947 burn there, and I'll show you some of that for four of the permanent plots. We'll look at the various types of fire activity that we have on the Kenai. And then we'll bounce back into the past and we'll look at a very long period of drought, about 5,000 years of very dry climate. And I think we are headed back toward that degree of drought now. So that will be a theme that I'll develop here at the end. And I think that drying has already started in 1968. And part of that drying will be the end of white and Lutz spruce that we have on the Kenai. And then what will replace that? That's the big question. So one possibility is that we will become a grassland or savanna. And another possibility is that it might be hardwood forest under an intense fire regime. So here is the Kenai Peninsula and the Kenai National Wildlife Refuge, and we're focused today on the western side there, west of the mountains. Those mountains provide a dramatic rain shadow. You can see the Harding ice field over there in Prince William Sound further to the right has captured the precipitation, and not much gets over onto the western Kenai, and that's why we have the potentially extreme drying situation. Well, in terms of fire activity, you can see on this map that the fires are mostly on the northern end of the western Kenai. Not very many down around Kachemak Bay here. The 1947 burn is our second biggest fire, and we'll look at that in detail. And then over here to the left, the west of it is the 1969 burn, a very severe mineral soil exposing fire. Well, since the new century arrived, we've been having more spring dry grass fires. And moving a little bit further south, the Caribou Hills fire, you can see there is moving into the southern Kenai. So this is something new here, and they raise the possibility of fires that essentially fertilize the grass and allow the development of a savanna or grassland condition. Well, we've had since in the last couple of years, a couple of large fires there. That Funny River fire is the largest fire that we've been able to document. And then last year, the Card Street fire. But both of these, again, were spring fires that don't seem to have exposed much mineral soil. So we've done a lot of fire history work on the Kenai here. Probably the first effort was looking at black spruce, which is a very flammable fuel type. Many of the fires up in the interior are burning in black spruce. And Andy DeVolder, in his master's thesis, looked at fire scars on black spruce trees and had about a 300-year record, and figuring the fire return interval was averaging about 80 years between fires. Then we had a much longer record, about 13,000 years, done by Scott Anderson. This was a lake sediment charcoal. We took a 7-meter core out of Paradox Lake, there in about 50 feet of water, and analyzed that in detail, and we'll go over that record, both for the pollen and the charcoal in it. But in the last 4,000 years, the fire return interval in that sort of mixed hardwood spruce forest was about 130 years. Before then, it was probably twice as frequent as that. And the third method was using soil charcoal. Basically, we did this in the southern peninsula in the areas that were logged. Birch trees were left by the loggers, and then they would blow down and turn up a nice throw mound, and we would look for charcoal there in the throw mount. And we found that really in the southern Kenai, the forest did not burn very often. The fire return interval was like 400 to 600 years, and there were some stands that we looked at that hadn't burned for 2,500 years. So fire is rare on the south end of the peninsula. Well, here is a grand overview of the Northern Hemisphere temperature records, just to kind of introduce you to some of the time periods and the terminology. This is from the Greenland Ice Core. They have about 110,000 year record. So we're looking at the last 22,000 years, kind of the top of the core there, but since the end of the last glacial period. And one of the notations that I use is Ka. You'll see down here on the bottom scale. That's 22,000 years, 18,000 years. And Ka means kiloannum. It's sometimes just easier to do that and write out all those zeros. Well, how much colder was it in the last glacial period? Really not a whole lot colder. The reference, now this is like the 20th century reference line up here, 0. So, we were maybe 4 degrees centigrade or 7 degrees colder. It really doesn't take a whole lot of coldness to bring on a glacial period. These dates here, Schielak, Moosehorn, Kili, Elmendorf, are some of the glacial advances that we have seen on the Kenai. They're occurring during a warming period. Warm weather can sometimes bring more snow and more ice accumulation. Then there's the younger Dryas period that's seen all over the Northern Hemisphere. Was a cold snap. There, just when people thought the glacial period was really ending, it took a turn for the cold again. But then after that, it warmed up, and we have this boundary here at 11.7. The Holocene period is basically the post-glacial period, and we come into a warming period. You can see this long period, many thousands of years of warming. That's kind of how it was seen in Greenland. The warm period in Alaska didn't last that long. It was more this 11.5 to 9 Ka. But basically, it seemed to have started in Alaska and then moved eastward. There's on the east coast and probably Greenland. It's lasting longer. We had a little warm period, a medieval warm period here when the Norse settled in Greenland, and then we have the Little Ice Age when the Norse were frozen out of Greenland, dipping here And now you can see we're up to about this point here, and then the forecast is bringing us, like 3 degrees centigrade or 5.4 degrees above the 20th century reference line here. And this is a moderate forecast up here. I mean, it could be a good deal warmer than that, especially if business as usual is continued in the burning of fossil fuels. Well, okay, so here's a brief view of the vegetation response. This is one of maybe the oldest pollen record that we have, Hidden Lake, a core of lake sediments. They're about 3 meters long. And it shows the arrival of birch here at 17,000 years. Before then, we're looking at basically grass, graminoid, sage, artemisia, and herb, a tundra environment. And then dwarf birch is rolling in big time here at about 17,000 years. We see alder coming in quite well here at about 11,000 years. And then as the climate begins to cool a little bit, white spruce is moving in here. And then later on, we'll see another record from Paradox Lake where at about 4,000 years, black spruce is moving in. But all of these shifts in vegetation are in response to climate change, as we'll see. So I want to look now in more detail at the two big historic fires. We'll look first at the 1947 fire, which I like to think of as a normal fire. It occurred during an ordinary summer. It burned all summer because they really didn't have very many people to put on this fire. So it kind of went its own way, and 110,000 acres were burned in there. Now, in 1969, the fire to the west, there was a Swanson River oil field at stake, so there was a lot more motivation to jump on that, and a massive number of cats and people were put on it. Millions of dollars were spent. So, 3 years after the burn, the refuge staff decided to set up some permanent plots to monitor the forest regrowth in the 47 burn. And these are along Ski Lac Loop Road here, which really doesn't show very well on this map. That's the Sterling Highway to the north and Ski Lac Lake. So 9 plots were picked, and these were not random plots by any matter of means. They were subjectively picked to represent a particular vegetation type like black spruce or aspen, and then a particular degree of burn severity as well. So we have, both light and severely burned fires. And I think they did a pretty good job of picking representative stands, to demonstrate this. But it makes it impossible to, draw any real statistical conclusions from it. I mean, ideally, you would like to have maybe 20 of each type there or something like that before you could do any statistics with it. Well, this was the system that they used to monitor. Each one of these little squares, 6 by 6 feet, is a millicre, 1,000th of an acre. So it takes 1,000 to make an acre. And then there were 10 millicres oriented in a north-south direction. So here's a photo showing the wooden frame with the strings and the little nails. So you can string this thing up each time you put it down. There are rebar posts there that go through a hole in the corner. And basically you can position these things, pretty much the same each time. And then you count, well, most of the plants are counted individually. And I use a little tally clicker, and then, ideally you can divide this thing into 100 squares with the string, and then you just go click, click, click with the counter, and they count fairly fast. Now there's some things like moss, where a cover value has to be estimated, rather than trying to count each particular plant. Well, I'll show you 4 examples of the 9 plots. This is a very simple example here. This was a young black spruce stand that was lightly burned. So mineral soil exposure, 0% there. And you can see that the black spruce here, recruited, and then it kind of leveled off, and then a few more have been picked up here, but basically it's been pretty stable. There was an early blast of cottonwood into this, but none of that survived. Just an interesting case. It's really the only plot that I think showed much cottonwood response. The grass and the fireweed took off very well, but they subsided in time as the canopy closed. So on all of these slides, the canopy is closing in the 1970s and beginning to shade things out quite a bit. And so then you see the moss takes off. It's 90% moss cover and some lichen growing on that as well. So here's a picture of what the ground cover looks like. You can see, almost 100% moss ground cover, and then Peltigera lichen growing on top of that, and some bunchberry, and then so forth. Well, in plot number 3, there was a terrific flush of aspen suckers. You can see, almost 400 aspen, and these are root suckers, clonal propagation. There, the trees were killed, the stems were killed, but not the roots. So the energy is going into putting up, new shoots, suckers from the roots, and it's really prolific. But they drop off with time. Self-thinning is going on, and now there are only 9 left on the plot down here in 2015. You can see there was fairly abundant grass and fireweed, lupin in the early periods as well. But again, those have all been sheltered out, by the closing canopy. And the ground cover today is basically leaf litter, and that suppresses the moss and the lichen. Well, in number 5, the burn severity was quite high, 60%. This is not quite up to the 1969 burn, where it was like 100% over thousands of acres, but it's still pretty high. And you can see the black spruce recruits here. There's also birch coming in here, recruiting on that exposed mineral soil, but dropping off with time. The fireweed starts off quite strong here. Probably this is clonal propagation from the unburned part of the ground cover. The 40% remaining. It would be interesting to look at the genetics of that to see whether the fireweed was clonal or whether it was individual plants from seeds. One thing that the surveyors did keep track of on these plots was with the aspen, whether the aspen seedlings were suckers or whether they were seedlings. And the suckers would be quite large, might be 2 feet tall, where the little seedling might be, 3-4 inches. So it was a pretty obvious difference, but they did keep track of that in the surveys. Well, the moss is doing quite well here. You can see 80% cover, so pretty thick at this point. Now, number 8 is another moderately burned, 35% mineral soil exposure. This was a birch stand with some white spruce. You can see the frame here is deployed around this birch tree, and then here it is here, and it's still here, but it's down on the ground by 1995 there, and it's hardly discernible at all by 2015. You could see there was an enormous amount of birch seedling recruitment. Again, this is on the mineral soil, the bare soil. 2,000 seedlings on the plot, but now only 14 birch remaining as adults. There was an alder flush on this plot as well. You see that here, but again, no alders today. So this is one of the beauties of having this historical data. I mean, if you go there today, you would never know that it had gone through an alder flush like that. It's just, you know, there's nothing left to record that. Okay, well, what happens after a fire and then the forest grows up? Basically, a lot of that tree recruitment takes place, you know, in the initial years, and then it slows down. And so on the Kenai, we would expect that the forest would reburn and the cycle would start again. But on the southern Kenai, where we don't have much fire, the forest becomes mature and the trees fall down and they produce nursewood. So here are some, you know, really nice examples of nursewood. These are hemlock trees from the Pacific Northwest, and this forest has probably never burned. But you can see how the hemlock germinated up in the air, you know, on top of logs and stumps, and then they put down those roots and are doing quite well. Most of the trees on the southern Kenai germinated this way, and they have the stilted root appearance that you see over here on the right-hand side. It's often possible to stick your hand down in a hole there between the roots and pull out the old nursewood. And here's a simple example, a little baby spruce growing on a nurse log 10 years after the Windy Point burn. Well, okay, looking now at a more extreme kind of fire, the 69 burn. This was basically produced acres and acres of mud. They're exposed mineral soil. And the birch recruitment on this soil was just phenomenal. And as a result, this became the #1 moose hunting area for many decades, and probably still is the best moose hunting area on the Kenai. And then hares, of course, loved all the birch. And then everything that eats moose and hares. You know, the raptors and wolves and so forth. So it's probably the most dense wildlife area on the Kenai Refuge. And of course the hunters loved it too, so it's, you know, fairly dense with hunters. The weather conditions for that were really quite dry at that time, just looking at the monthly precipitation here. And then the temperatures were quite warm. So this was the second summer of drought with a dry winter in between, and it was really very dry. And then it had wind-driven fires as well, so it was kind of a tough one to put out. Here are a few examples of the exposed mineral soil that you see there that provides just this beautiful bedding spot for the birch seeds, which are distributed in the winter and then germinate in the spring. A satellite vegetation map here, 2011. You can see the 1969 burn. The yellow colors are deciduous, you know, hardwood forest, and basically birch in this case. And then here's the 47 burn, you know, much bigger, but much darker green with conifer forest, although there are certainly areas here of the deciduous forest that were probably more severely burned. Well, okay, so essentially we have 3 types of fire on the Kenai. We've looked at number 2, the normal weather type, 47 burn. We've looked at number 3 here, the extreme burn severity under very dry summer conditions. And then we have this more, shall we say, recent type, the dry spring fires that are often pre-green up. The grass is dry, and you get like a very dry May and a bit of wind blowing, and you can have quite the fire developing quite quickly, and these can be scary fires. Well, here is the Caribou Hills fire, 2007, and this is 8 years later. Photograph, you can see that the fireweed in the grass is really doing terrific here. Now, when these spring fires occur, the soils are typically wet or even frozen, so there's very little mineral soil exposure. And the soil gets a terrific pulse of ash from the burned vegetation, so fertilized. And basically the grass and the fireweed takes off after that. So we're thinking, if we get enough of this kind of fire going on, this might convert this landscape to a grassland or a savanna. We also have a lot of logging that has been done, especially west of the Kenai Refuge or the Native Corporation lands. And the grass is doing very well now. It's getting a lot of light, and one wonders, is this a potential grassland? I mean, there is some spruce recruitment going on, you can see here, but an awful lot of this area, is pretty extensive grass, and of course it will support those early spring fires. So the effect of logging is kind of similar to the effect of the spring grass-driven fires. Okay, I'm going to step back now to the paleo record and see what we can see of these kinds of fires in the pollen and charcoal record. So here are some of the lessons that I want to bring. That first, that the landscape vegetation can be stable for thousands of years despite repeated burnings. I mean, it can be a spruce forest or a birch mixed forest, for thousands of years and get burned repeatedly and come back the same thing. We'll see that vegetation changes when the climate changes, on a large scale. We'll see that grass has always been a very minor player according to the pollen record. We'll see that there was an extremely dry period between 14,000 and 9,000 years, and that hardwoods reigned supreme at that time. And we'll see as the climate cooled and got wetter, that it brought first white spruce and then black spruce. And then we'll see once again that the Kenai is in a long-term drying trend, and my hypothesis is that we are headed back toward another drought on that same order of the 14,000 to 9,000 year period. Well, here is a detailed record of the pollen in Paradox Lake. This is almost a 13,000 year record, 7-meter core. It doesn't go back quite as far as that Hidden Lake record that I showed you that went back to 17,000. So when we look at the birch at the bottom of the core, it's already going full bore here. So this is a shrub tundra period here. And then about 11,000 to 10,000 years ago, alder comes in big time here. And we're also seeing populus, which would be cottonwood in this case rather than aspen. And we're seeing willow taking off as well. So hardwoods are moving in big time. And then a little bit later, tree birch gets underway here as well. And then about 8,000 years, we see white spruce coming in here. And then kind of 4,000 to 5,000 years, we see black spruce. Now, black spruce, probably did appear a little bit at the same time that white spruce did, but it really is taking off more here. And there's a definite cooling and wetting of the climate that's taking place at that point, which you'll see in a minute. Okay, here is the charcoal record from that core, that 7-meter core. And basically the charcoal is being analyzed in little 1 cubic centimeter segments of the core, so 7 meters, 700 samples, and calculating that, or measuring the number of charcoal particles in that. And you can see at this period here, the charcoal particles are particularly dense. So this represents a high fire frequency period here. And that information is reinterpreted in this graph here. So here we're looking at a fire event frequency of 10 to 12, 14 fires per 1,000 years here. And on the left, from that charcoal measurement here, again, one can calculate in a cubic centimeter of charcoal how many particles, per unit time were being deposited. I mean, if you know the time span that cube of charcoal or cube of sediment represents, you can calculate that deposition rate. And you can see that rate varies. This is a logarithmic scale, several orders of magnitude down here at the bottom. Well, for a temperature record spanning this period, we have this temperature record here. This is based on pollen. This is not from Paradox Lake. This is, I think, from a Sirius Lake, lakes in southern Alaska. And the way you reconstruct temperature from pollen is looking at the proportion of warm-loving plants versus cold-loving plants. And during the warm period here, the hypsothermal period or Holocene thermal maximum, there was a greater proportion of warm-loving plants than cold-loving plants. And then here, as the climate cooled, the proportion shifted and the cold plants came to dominate. I wouldn't say this is a perfect curve here. It's a little too detailed, you might say, but it does show the general warm period of the hypsothermal here, and the cooler later period, neoglaciation as it's sometimes called, because there was glacial advances in the mountains in many places during that cooler time. Now, we can just to get oriented, 57 degrees is the Sterling July temperature at the present time. That hypsothermal maximum is about 61 here. And then the forecast mid-range emissions scenario is 62 degrees by 2100. At the end of this century, they're forecasting 5 degrees warmer temperature than the present time. And this is from the SNAP, the Scenarios Network for Alaska Planning Group at UAF that makes these forecasts for specific communities. So I've looked specifically at Sterling there, which is kind of in the center of the Kenai Refuge. There in near Paradox Lake, for instance. Well, okay, so I've added now the fire record and that temperature record to the pollen record that I showed you before. And the pollen record can be divided into these vegetation zones, you might say, starting with the dwarf birch tundra, and then moving up into the hardwoods here, and then spruce and birch recruiting here, and then black spruce being added for the kind of the modern form. But the forest has been in probably the present form for the last 4,000 years. And as you could see before, well, over here, it's burned repeatedly during that time. And, you know, it's always, you know, come back pretty much the same. There hasn't been any kind of type conversion because the climate really hasn't changed too radically over the last 4,000 years. Okay, now over on the left, I've added a lake level record so that we can have some idea about the amount of water. You know, how wet is the situation here? And this is a new part of the story. Most of this lake level work comes from work that I've done since I retired here, a lot of peat coring. And it's showing this very dry period here where lake levels are really way down. And I want to take a bit of time to explain how I determined that curve. So I use satellite fens. These are little, you know, peat bogs or fens, properly speaking, that are around the edges of lakes. So here you can see one. This is kind of what it looks like on the ground, and the lake is not very visible in the background. Here's a LiDAR image of the same thing. So we're down here at this end, but and you know, any one of these places would have been interesting to take a core, and I probed with a rod to find the deepest spot, potentially the oldest core. Now notice that this LiDAR image shows up very nicely a shoreline here at 68 meters, and that's about 1.5 meters above the modern water level. And the modern water level is constrained by a little outlet here. So I think this is a new outlet. I think that this was a closed basin lake for most of its history. And then probably in the last 4,000 years with more wetter climate, the lake level rose enough that it was able to cut this little outlet right here. But you can see how narrow this is. Okay, now here is sort of a concept example that to explain how I determine where the lake level was in the past. So let's say we have one of those shorelines up here where the shore has been eroded and cut a distinct scarp. And let's say that's at 70 feet. Then we have a satellite fen here, and this is terrestrial peat in it. And that examination of the peat to be sure that it is terrestrial. So we take a peat core here, and we go all the way down to mineral soil. And then we get a date at the bottom of the peat here, and let's say it's 12,000 years. Well, because this is terrestrial peat, the lake level had to have been drawn down to that level at 12,000 years. Now, it might have been drawn down more. So we're talking about, you know, down to 50 feet, 20-foot drop, but, you know, maybe it was down 25 or 30 feet. I mean, this is, you're just getting the elevation of this bench right here. So I probe and I try and find the deepest place to probe, but as I say, this is an estimate of the maximum possible lake level, but it could have been lower. Well, peat coring is kind of a grunt operation. There's two of my graduate students. They're punching away. We're getting a 3-inch core, piston Livingston core here. This is an example from Rainbow Lake. This is drive number 7. We finally hit the bottom. We got down into mineral soil here, clay. And a basal date on the peat here is 11,300 years. And careful examination of the peat here shows this is sphagnum and other terrestrial peats, so that it's not lily pads or aquatic vegetation. Okay, so I've looked at 8 lakes in some detail here, and on this graph we're looking at time down here at the bottom, and then we're looking at depth below those shorelines, those wave-cut scarps. So how much did it drop? Well, the example I showed you, was 20 feet. So you can see a lot of these have dropped about 20, I mean, even more than 30 feet. What we don't know is the age when the scarp was cut. It's very difficult to age erosional deposits. I mean, things are taken away. So you have to normally find something that was deposited after the erosion event, and then that gives you kind of a minimum age estimate. But we know that the deglaciation was occurring around 18,000 years ago. So I picked that point here. But these dates down here are very well determined with radiocarbon. And this particular curve here is a series of dates in the deepest core from Jigsaw Lake here, which was about a core that went down 26 feet below the old shoreline around Jigsaw Lake. But it's showing, quite a remarkable drawdown of all of these lakes. I mean, every lake that I've looked at, it shows this drawdown. Okay, so that's how I got the lake level curve over here, and it does, give us, I think, further information about the climate. That this was a very dry time, so we have the fire activity, is picking up in this time right here. There is probably a lot of mineral soil exposure going on, and that's why the tree birch here was able to take off so well, and the alder. I mean, both of those like exposed mineral soil. So this is a period of hardwoods associated with this very dry time. And essentially, I think we are headed back toward a time like that, where we will see, again, a high level of fire activity and extreme mineral soil exposure and recruitment of birch on top of that. Well, here is the most recent part of the story, the drying that is underway on the landscape now. So you can see these are closed basin lakes where the water level has dropped a meter or more. And here is a wetland. You look at a forest like that and you think, oh wow, that's some old black spruce stand. Those trees have been there for thousands of years and so forth. Well, we ran a transect, 2-meter wide transect through there, and we found out that these trees are young. The median age was 32 years. When we would dig down in the peat, and there was more than 15 feet of peat in this, there wasn't any wood underneath. There were no stumps, no buried logs. So this is a new forest, and most of it started recruiting within the last 80 years. And many wetlands on the Kenai are like this. They show a halo of black spruce around, and in some cases, the entire wetland has been covered with this. But this will affect the fire regime, because in the past, the wetlands were fire breaks, but now that they're being covered with black spruce, they will become fire bridges. It will bridge the fire from the upland area, across a lowland to the next upland. Well, we can see, why this is happening in our weather records. This is Kenai Airport data here, and what I'm showing is available water. And I like to use available water rather than just precipitation, because available water is the water that is available to use on the landscape. So that is calculated by starting with precipitation, annual precipitation or monthly precipitation, and then subtracting the calculated potential evapotranspiration that would be due to evaporation from the plants breathing out water, transpiring water, and also evaporation from the soil. So thinking of this in a monetary example, people, you have an income, and then you have basic expenses, and the money you have left over, that's your available money. So available water, after you've transpired your expenses that way, you have available water for growing the plants, the animals, for recharging groundwater, for funding stream flow, and so forth. And so it's really the usable water. Well, you can see it declined pretty dramatically after 1968 and 69. I mean, we never recovered from that drought there. The 69 burn was here. If we look forward with the SNAP forecasts, they come down to about 0 inches of available water by 2100. That's not the end of the world. As long as you get enough water coming in the spring, the plants will grow, even if you have a dry summer. Anchorage typically runs a negative water balance, maybe an inch and a half or something like that. So life does go on. Now, it could be much more severe than forecasted here. And we're only going to 2100 as well. But climate change goes on, well beyond 2100. Well, okay, so how does this affect the vegetation and the fire activity? And specifically, what happens to the white and the Lutz spruce, where we have drought stress and bark beetles? Okay, well, Glenn Judet essentially made the argument that white spruce will go extinct up in the interior, and he was using tree ring evidence for this. On this graph, temperature over here on the left is increasing downward, so it's warmer going down and colder going up. But he's showing temperatures reconstructed from tree rings here, which are in the green. And then here are future climate scenarios. I mean, 2 different scenarios are shown, and how they affect the ring width over here on the right-hand scale. And you can see on this scenario here, the ring width is going to 0 by 2100. So this is pretty much the end of white spruce if that scenario obtains. I mean, it's 0 growth. And 0.4 millimeter is not a whole lot better. So drought alone would probably be sufficient to extinguish white spruce. Okay, then we add in the spruce bark beetle, especially in southern Alaska. And we know that if we average summer temperatures and take the past 2 summer temperatures, there's a threshold here of almost 51 degrees, where when those 2 summers average 51 degrees, then one starts to see a lot more beetle kill acres appearing in the annual surveys. So you start seeing a forest that looks like this. Really a very distinct threshold there for the beetles. Well, on this graph here, looking at temperatures, these are the past 2 summer means, and these are projected future ones according to 3 different climate models. And we are up here from last summer, so we're well above this 51 degree threshold. And essentially this means that in the future, the summers will always be above 51 degrees. And any tree that is big enough to be attacked by the bark beetles, will be attacked. So we'll never have large Sitka, Lutz, white spruce forests again. I mean, we could have pole-sized forests that could be cut for pulp, but the beetle will set a limit on how big they get. Okay, I'm going to show you some modeling now, and this is just a basic map to get oriented. Our forests on the Kenai are classified as this boreal transition zone, all of southern Alaska here, and this very sharp line between the North Pacific Maritime and the Boreal Transition. I mean, this is the edge, the front of the Kenai Mountains here. And it's pretty wet over here on the east side. That's catching the rain, and then we're in the rain shadow here, and in this area more generally, but especially on the Kenai, we really, it's sort of the immediate rain shadow. So I'd like to present now a look at the future here, since we've seen so much of the past. This particular modeling is called niche modeling, and I'm going to show you a series of slides that will go up to the end of the century, projections of this modeling, and then I'll go back through it again so you can see it twice. What is being modeled here is what vegetation could grow according to the climate, not necessarily what is there at the moment, but it's what could grow. So you can see the gray area, much of the western Kenai is this boreal forest with coastal influence and intermixed grass and tundra. So like the Caribou Hills might be tundra, the Kenai. Now we also have a little bit of prairies and grassland up there in the northwest corner of the Kenai. That isn't presently grassland. It's hardwood forest, 69 burn, like we saw on the slide, but it could be grass and prairie if we just started from scratch there. So the present climate would permit that. And okay, so now we go forward to 2039, and you can see that prairies and grassland is expanding quite a bit. It's coming down the peninsula and expanding northward from Anchorage. 2069, it's expanded quite a bit more. Caribou Hills are still boreal forest with tundra, so forth, but by 2099, pretty much all of the western Kenai is in the prairies and grassland niche. And notice that southwestern Alaska is very much showing the same vegetation possibility as well. So let me run through that again, just so you can see it. 2009, 2039, 69, and 99. So this is a strong argument for saying that the western Kenai could become a grassland. Now, an entirely different style of modeling using the random forest platform, work of Don Magnus here at the Kenai Refuge. The baseline on the left is showing the vegetation as it is now. I think just 10 veg types. It's similar to the satellite map that we looked at, showing the two big burns. You can see a lot of, in the northern part, the conifer, black spruce, and then that's projecting forward to the end of the century, becoming more hardwoods. But the transformation on the southern end is more striking, because there the kind of the background color here is white Sitka spruce or Lut spruce, shrubs and alpine, and that is shifting to a different, a light gray color here, which is essentially herbaceous or grassland. So again, this is another argument for at least the southern part of the Kenai Peninsula becoming a grassland. Well, I have an alternative hypothesis because of my work on the lake levels, that I have seen just how dry it can become. Before I had the lake level record, I had no idea that this place could dry out to the degree of lowering lake levels, 20 or 30 feet. So my conjecture is that we are already started on this trajectory toward a drier, much drier, western Kenai. And the fire regime accompanying that, of course, will be much more frequent fires. The fires will be more widespread because we now have black spruce in the muskegs, which will bridge the fire over the uplands. So it'll be possible to quickly burn large areas. And then because of the dryness, the degree of burn severity will be much greater. And that there may be grasslands there, but extremely severe fires will simply burn out the grass and expose the mineral soil, and then birch will recruit after that. So kind of to conclude, I'd say we've have strong evidence on both sides here, the modeling, looking for a grassland and a hardwood forest based on the prehistoric record, shall we say, of the extreme drought. And it could be there's just a difference in timescales here, that we may well go through the grassland period. These climate models that I showed you, only go up to 2100. That is within the lifetime of children being born today. We'll see that. Climate warming will continue to go on, for many centuries, and I don't know why the modelers don't run those models out to 2500 or something, but they're scary enough to run out to 2100, I guess. But I have a longer term view of it, so I'm thinking that it may take several centuries to dry out the Kenai well enough to get the conversion to hardwood forest, but I'm forecasting that it will come. So that is the end of my talk today, and I thank you very much for joining me.